Okay, hey folks, picking up right where we left off. I think that this should be the last video of our section on phase changes, but I've got a timer going, so we'll see how long this goes. It might end up being 2 if it goes too long. Okay. But now what I want to get into is how we can start predicting mathematically where these phase boundaries should appear. Okay. So for example, I'll remind you that when you look at chemical potential versus temperature, right, the slope of this line is entropy, right? And we noted that the vapor has a bigger entropy than the liquid, than the solid. So where we see these cross, that's where the phase transition happens, okay? So I derived an equation on the first lecture that was chemical potential as a function of pressure. So chemical potential of P final equals chemical potential of P initial plus RT natural log of P final, P initial. And in the case when P final is greater than P initial, if we just think about this and inspect this equation for a moment, then this means that mu will increase, right? Because if P final is greater than P initial, natural log of a number greater than 1 gives me a number greater than 1, right, times RT. And then that has an additive effect, right, because I get a positive quantity, okay? So when I increase the chemical potential of these, then I'm going to start seeing lines that look something like this. You know, maybe my solid line, it increases, okay? And then my liquid line, it increases, okay? And then you can see where they cross, I get a new melting point, okay? And so just as a general rule, if I look at this for 2 cases, okay, and here these are cases in which the density of the solid is less than that of the liquid and the density of the solid is greater than that of the liquid, okay? So in this case on the left, this is a case where I'll say the molar volume of the solid is less than the molar volume of the liquid. So this is normal, right? So this is a normal condition, most things, where the solid is more dense than the liquid. Or in other words, the molar volume of the solid takes up less space, right? So for the same amount of material, that means it's more dense. So what you see here is a smaller effect on the increase of the heat capacity of the solid, but a much bigger increase on, I said the heat capacity, rather, I meant the chemical potential. But there's a much bigger increase of the chemical potential of the liquid. And as a result, you notice here that the freezing point increases. So that is, most materials will have an increased boiling point with an increased pressure. So let's say as P increases, TF increases. But now this is a case in which the molar volume of the solid is actually greater than the molar volume of the liquid. So this is totally not normal. In other words, water, right? And so now what you notice, the effect here is that there's a much bigger increase in the chemical potential of the solid than there is of that of the liquid. And the result here is that the freezing point decreases with increasing pressure. So as pressure increases, the freezing point decreases, okay? So this is the case with most things. In other words, the solid doesn't really change that much with increases in pressure, which is kind of what we would expect. However, water is strange. Water is weird. And in this case, there's much more of a change to the chemical potential of a solid than there is in the liquid. And that's really what's driving those things for water, okay? So now